So in some of the earlier videos we talked about addition to alkenes, all right? And so just as a reminder, addition to alkenes is when you add some chemical to an alkene and all of the atoms of that chemical end up getting added to the molecule, all right? Meaning every single electron that was in that original molecule, every single atom that was in there, you'll find in that in the new molecule. All right. So there were four types of addition reactions. They were hydration, hydrogenation, hydrohalogenation, and halogenation. All right. So the first thing I want to do here is talk about the mechanisms of three of these. All right. We're not going to talk about the mechanism of hydrogenation because it's fairly complicated. But for hydration, remember what hydration is that is the addition of water to the double bond. All right. So in order to do the hydration, you generally need to have a strongly acidic aqueous solution. All right. And the reason that you need strongly acidic solution is that the first step in the mechanism is that an electron pair from this double bond has to attack that hydrogen to create this, what you call a carbocation intermediate. All right. So let's say that two of the electrons from this double bond attack this H plus. All right. That would create this intermediate right here. And we're just going to assume that the bond that gets formed is going to be between the right carbon and this H plus. All right. We'll talk more about that. The differences in which carbon does the attacking in it a little bit later. All right. So after that, this intermediate gets formed. An electron pair from the water attacks that carbocation. All right. Again, in this situation, the water would be acting as a nucleophile. The carbocation would be acting as an electrophile. All right. So that would then create this particular intermediate right there. Notice that when that happens, the positive charge is no longer on this carbon. All right, it would actually be on this oxygen right here. All right, notice that there's two electron pairs here and that the oxygen is neutral. Notice that here there's one electron pair, all right, and that there's a positive charge. All right, the other electron pair is now the electrons that are forming that went into the making of this bond right here. All right, so then just some water molecule that's close by. The electron pair is going to attack that H plus. This electron pair is going to go back onto that oxygen, and that's going to release the overall product right here. All right, and one other thing that's going to make is H3O plus from when the water attacks that H plus. All right, and so remember H3O plus is the same thing as H plus, and so this goes on to become the H plus that another one of these alkene molecules would attack. All right, so the reaction would just keep on going. All right, so notice here, this is the product of the hydration. You have essentially taken this alkene right here and you've added H2O to it. All right, if you looked at a water molecule and you looked at this thing right here and you counted all the electrons and all of the atoms, you'd find that every single electron and atom is accounted for. All right. So the mechanism for a hydrohalogenation is fairly similar. First, we're going to have your alkene attacking the HBr in a fashion such as this. All right. Again, that would form a bond between this carbon and that hydrogen, but that's going to create a positive charge on this carbon right here. All right. So this bromide ion, which got formed when these electrons went onto the bromine, is then going to attack that carbocation, giving us the product right here. And the last mechanism is going to be for the halogenation. So you get attack of this bromine right here. These electrons go onto this bromine, creating a bromide ion, which then attacks that resulting carbocation, giving this product right here. All right. So again, we did not do a mechanism for hydrogenation because it occurs through a slightly different mechanism. But notice there's a similarity in all of these mechanisms here. You get an initial attack of one of the electron pairs from the double bond to some atom that creates this initial carbocation. All right, so you've got a carbocation in each of these species right here, and then some anion then attacks the carbocation to give the final product. All right, so you can see that in all three of these cases. All right, so the first thing I want to point out is that what ends up happening in these reactions is different when you have a symmetrical alkene versus when you have a non-symmetrical alkene. All right, so what we mean by a symmetrical alkene is if you were to take the double bond and just basically think of a mirror going between the two carbons here. If you've got the same two groups on the left side as you have on the right side, it would be considered symmetrical. All right, so let's say, for example, these two are hydrogens and these two are methyl groups. All right, that would be symmetrical. All right, because you would have the same groups on each carbon. All right, you could also argue this would be true. It would be considered symmetrical even if these were trans. All right, so if this were a methyl and this is a hydrogen, and this is a hydrogen and this is a methyl, all right, we would still have, as long as you had a methyl and a hydrogen over here and a methyl and a hydrogen over here, we could still make the argument that that would be symmetrical. All right, so this is why this matters. All right, what we're going to do, what we need to realize is that in that first attack step, all right, remember we had to form a bond between one of the carbons and that initial atom. All right, and when I was doing the mechanisms here, I just arbitrarily chose the right carbon. All right, notice that bond was always made to the right carbon. All right, but notice we could have made that initial bond to the left carbon. All right, so that's what I'm going to do here. I'm just going to show the mechanism for the two different situations. All right, here we're going to make that initial bond to the left carbon. Here we're going to make it to the right carbon. All right, so if we make it to the left carbon, notice that creates the carbocation on the right carbon. And if we attack the right carbon, it creates the carbocation on the left carbon. All right, so when we then add our other atom, all right, let's pretend that it's, in this case, it would be bromide. That would mean that would put the bromide on the left carbon. Here we would put the bromide on the bromine on the right carbon. All right, but notice what happens. All right, no matter which of those original carbons made that first bond, you ended up getting the exact same product. All right, and that's why the situation with symmetrical alkenes is going to be different than when you have non-symmetrical alkenes. Because if your starting alkene is symmetrical, if you have the same groups coming off this carbon as you do off this carbon, then you're going to end up getting the same product no matter what. And what we're going to do next is contrast that to the situation where you have unsymmetrical or non-symmetrical alkenes. So what happens when you have a non-symmetrical alkene? So I'm just going to use this compound right here as an example. Okay, so this would be 2-methyl-2-butene. All right, so what's going to happen here is we're going to consider the two different situations. All right, so let's pretend, for the sake of argument, that the original bond that forms that undergoes addition is going to form a bond to the right carbon. All right, that would end up creating this product right here. All right, if it attacked the initial bond was made to the left carbon, if we got that hydrogen off this one, that would create the carbocation here. The bromide would attack that carbon, that would create this product right here. Notice that the two different products that get created are different from each other. All right, and that's because what creates this is which of the carbons undergoes that initial attack. All right, and that's significantly different than if you have a symmetric alkene, because no matter which of the carbons did the original attack, you ended up with the same product. All right. So the thing is, even though we could draw mechanisms that would show two possible products, sometimes you'll get two products. Sometimes it could be 50-50 with those products. Sometimes you might get a major product and a minor product, and there are some situations where you would only get one product. All right, so we're going to talk about what causes that there to be a preference or not to be a preference. All right, and that's going to be governed by what's called Markovnikov's rule. All right, and it says that during an addition to a double bond, the hydrogen is going to end up becoming bonded to the carbon with the most hydrogens, while the other atom is going to be added to the carbon having fewer hydrogens. All right, and hopefully this makes sense when I show examples of this. But really quick, the underlying reason for this is that the mechanism requires a carbocation intermediate, and the order of stability is that the tertiary carbocations are more stable than secondary, and those are more stable than primary. All right, so let's take this product, this starting material right here. We're going to consider the two different situations. All right, and over here, we're going to say that the hydrogen is going to get added to this carbon. Over here, we're going to say that the hydrogen gets added to this carbon right here. All right, notice when it gets added to the left carbon, that ends up creating the carbocation on the right carbon, and that ends up making a secondary carbocation. All right, notice that there's two carbons attached to this carbon right here. Notice over here, you end up getting a tertiary carbocation. All right, that's because there are three carbons attached to that carbon right there. And the thing is, tertiary carbocations are more stable than secondary carbocations. All right, so you would then have the second step, the addition of the attack of the bromide. So the thing is, you would end up getting this as the major product. All right, you would probably still be able to make some of this. Some of this would get made, but just not as much as this. And the reason is because the tertiary carbocation is more stable, there's just going to be more of that. All right, there's going to be a better chance that the initial addition is going to happen to the right carbon, so that you would have that more stable intermediate get formed. All right. So let's consider another example right here. In this case, we're going to do a hydration. All right. So let's just say, all right, let's take this compound right here, and let's treat it under the standard hydration conditions, like some strongly acidic aqueous solution, and ask, which, if either of those products would get formed. All right, so let's consider the two different scenarios. All right, up here, we're going to assume that hydrogen gets added to this carbon, and down here, we're going to assume that the hydrogen gets added to this carbon. All right, so if the hydrogen gets added to the right carbon, that creates a tertiary carbocation. If it gets added to the left carbon right here, that would end up making a primary carbocation. And one thing about primary carbocations is that they are very unstable. All right, there would be an even stronger preference for this being the intermediate between these two than there was in this situation right here, because even though tertiary is more stable than secondary, secondary carbocations are still stable enough to exist in solution. All right, primary carbocations are almost unheard of. They are extremely unstable. All right, so this would be the only intermediate that gets made in substantial amounts. And when you add the water, so that I abbreviated this right here, I said add water, and then we're going to take an H plus away. And essentially what that's doing is just doing the two steps right here. We're going to add the water, and then we're going to lose that H plus. So that's just shorthand for these two steps of the mechanism. All right, and so when you do that, this is going to be the product that gets formed. All right, so if you were to do this reaction right here, this would be the only product. And you can explain that through Markovnikov rule, which has to do with the relative stability of the carbocations.